So in this lecture, we'll deal with classification of bifurcations, which can take place in one-dimensional flows. So we consider flow x dot equal to f of xc, flow is parameter c. So f is good enough function. It has continuous derivative for all possible values of x. So we assume 0, 0 is an equilibrium. Which means that f at 0, 0 equals to 0. This is first point. Then we know that if this equilibrium is hyperbolic, then we will not have there any bifurcation. We discussed it on the previous lecture. Therefore, we assume that this is non-hyperbolic equilibrium. Derivative of f over x at 0, 0 is 0. And now there is so if it is possible that this equilibrium is in fact corresponds to bifurcation in this flow. Let's consider first order approximation of our flow. So this is x dot which equals to f of x c. So this is first order approximation would be f at 0, 0 plus derivative of f over x at 0, 0 times x plus derivative of f over c at 0, 0 times c. Now what we know, it is equilibrium, this is 0. This is non-hyperbolic equilibrium, this is also 0. Therefore, x dot is roughly derivative of f over c at 0, 0 times c. What we have here? We have here that so let's say xc is equilibrium. Where if c equal to 0, x is any number, and if c is non-zero, no equilibrium. So this is, it's called degenerate case, degenerative. Case. So we either have infinitely many equilibria or none. And this is called non-local behavior. And this indicates that first order approximation is not appropriate. So we missed some very important information about dynamics in this system by taking its first order approximation. Therefore, what we should do, we should consider second order approximation. So now x dot will be equal to, so f at 0, 0 is 0, derivative of f over x at 0, 0 is also 0, therefore we'll just start with this derivative of f over c at 0, 0 times c plus all second order terms, half of second derivative over x at 0, 0 times x squared plus mixed derivative at 0, 0 times x times c plus second derivative over c half at 0, 0 times c squared. So this is second order approximation. Yeah, so I will put here. Now, here, since it is approximation, and approximations work for small values of x, we assume that x by absolute value very small and c by absolute value also very small. So if c by absolute value very small, let's put it like this, if c tends to 0, then c squared tends to 0 even faster. And therefore, half of second derivative of c at 0, 0 times c squared will be much smaller than derivative of f over c at 0, 0 times c. Therefore, can be ignored. So what we conclude is half of the second derivative of f over c at 0, 0 times c squared can be ignored. And same is true about mixed derivative. It's also much smaller than derivative over c at 0, 0 times c, since cx is much smaller than c, because c tends to 0, x tends to 0, and c is multiplied by something which tending to 0, therefore cx is much smaller than c, and also can be ignored. Now what we got is x dot is roughly equal to derivative of f over c at 0, 0 times c plus half of second derivative of f over x at 0, 0 times x squared. Now, if by any reason we will decide to ignore the second term, we will end up with first order approximation. To avoid this first order approximation, we should set certain conditions for x and c. So x tends to 0, we know this, it is small. C tends to 0, it's also correct. But now, in addition, we assume to make this term of the same order, x squared is of the same order as c. Then it's fine. Then we can do it. Now, so we will keep this term. So we will have these three terms. And next, what we will do, we will replace this derivative we denote by a, and half of second derivative over x we will denote by b. Therefore, we will have x dot equals to ac plus b x squared. So we got now, this is our second order approximation. I used a bit different, a bit longer arguments to come to this shape of our function, of our second order approximation. You can look at this in lecture notes, but what I presented here seems to be nicer and more concise at least. Now, what we do next? Next, we use substitutions. But before we do substitutions, we should make some further assumptions. So whatever we do, we want to keep direction of dynamics. So what it means? It means that we substitute x and c in a way that when x is increasing, x tilde is also increasing. And when c is increasing, c tilde is also increasing. So what we want to do, we want to keep direction of dynamics. So to keep directionality in the dynamics. So this is general comment, and now to work with this comment, we will consider a few cases for what we have now for parameters A and B. Cases depending on signs of A and B. So first case one, assume that A positive and B positive. If A positive and B positive, then we make the following substitutions. X tilde equals to bx and c tilde equals to abc. And when we put this, so we need to put it into our flow, approximation to our flow. X dot equals to ac plus bx squared. So if after putting it there, in terms of x tilde and c tilde, we will have, I will skip it, you can check it, x tilde dot equals to c tilde plus x tilde squared. So this is what we got. And then if we use return to previous notations, we will get x dot equals to c plus x squared. It's just changing notations. Now this x and c is not the same as it was before. And so we got as a first order approximation, this kind of, or the second order approximation, this kind of equation. And for this equation, we find fixed, also equilibrium. C plus x squared equal to 0, which means that x1, 2 equal to plus minus square root of minus c. So exist if c is negative. And finally, stability derivative of f of xc equals to 2x, and therefore derivative of f when x equals to square root of minus c equals to 2 times square root of minus c, unstable, and minus square root of minus c minus 2 square root of minus c, stable, it's negative. And therefore, this will look like this bifurcation diagram for this c x. So we have equilibrium only when c is negative, this is stable, this is unstable. So this is bifurcation diagram. So this is for case 1. So generally, again, we get back to x dot equals to ac plus bx squared for arbitrary signs. Signs of a and b, we will do the following substitutions. So x tilde equals to absolute value of b times x, and c tilde equals to absolute value of ab times c. So again, c is when c is increasing, c tilde increasing, when c is decreasing, c tilde decreasing, and same is correct about x. And now with this substitution, so when we substitute, put it here, what we get is this x tilde dot equal to a over absolute value of a times c tilde plus b over absolute value of b times x tilde squared. Or if we make get back to previous notations, we get x dot equals to a over a tilde. It's a is a plus 1 or minus 1, so we put it as plus minus c plus minus x squared. So this is called normal form for fold bifurcation. So in fact, we can have 4 cases here: plus or minus b4 parameter c plus or minus b4 x squared. And one case we already considered with 2 pluses. First case bifurcation diagram was this cx. Second case, so here plus plus. And in second case, you can check it. I will skip this. It is same procedure as was here. So again, cx, stable branch and unstable branch. And this case is minus plus. So minus means minus before c, and plus means second plus means plus before x squared. Then third case, cx, stable branch, unstable branch. It's again different signs, but it is plus minus. And last case, stable branch, unstable branch, cx, and this case is minus minus. So this pretty much completes story about fold bifurcation, and I will talk about two other bifurcations in the next lecture.